Getting to that point.
All right, so today we're going to, a couple things we want to do. First, we're going to go over the midterm, answer any questions you might have. We're going to go over, I'm going to hand back, well, I guess I emailed you guys homework 6 last night. We'll go over homework 6, also answer any questions on homework 7. And then my plan is to start talking about cryptography, so an application of number theory to encoding messages. So first, let's go over the midterm. Question 1 was fine. Question 2 was fine, I think. And some people struggled a little bit with number 2, part B, trying to find integers that add them up, and then, you know, I mean, you can do it the hard way, like you did, kind of using homework, using going back to the Euclidean algorithm. So a lot of people got -14, 7, and 1, but you could have just, some of the answers, some people just, I think they just figured out how to add up 6, 10, and 15, so you get 1. And if you just add 6 plus 10 and subtract 15, you get 1. So there's an infinite number of solutions to that part 2B. 3B, sorry, number 3 was, yeah, I said use the definition divides the number 3. So I think most people follow the directions. So, you know, 2b minus 3c squared, that's a linear combination of b and c. So, you know, you could, some people said like, well, a divides b, and then a divides c, so a would divide a linear combination. Well, that's not really that wasn't really the spirit of the question. I wanted to see, you know, I wanted you to use the definition of what does it mean for an integer to divide another integer, and then just work it out, use substitution. I think most people did that, and it was fine. Are there any questions about 1, 2, or 3? 2 or 3. All right, number 4, 4A was not solvable. 4B was solvable. And in general, those two, 4 was okay. Any questions about number 4? All right, number 5 is kind of surprising.
Me too.
So there was actually 17 possible answers. You could have, you know, I only asked for 3. One of the biggest properties of the OLE function is it's multiplicative. So phi of A times B is phi of A times phi of B when A and B are relatively prime. So that's the main thing that you had to use. That's the easiest way to solve this. I mean, you could have just sat there and trial and error and look for numbers and then try to compute phi function of that number. Some other things that, you know, we know, I reiterated this on last week's videos, but like for a prime, phi of p is p minus 1. So that's another thing you got going for you. So if you can factor 120, and there's a lot of different ways to factor 120. So like, think of 120 as just, how about 60 times 2? Well, if you can find a prime whose, you know, phi of that prime is 60, like 61 is prime, so phi of 61 would be 60. So 60, you can think of that as phi of 61, and 2, you can think of that as phi of 3. 61 and 3 are relatively prime, so you kind of build it up that way. So that would be what, 183. So that's how you do this a lot of different ways. You could add, you know, 60 times 2 times 1 would be 120 as well. So you could do this again. You could do phi of 61 times phi of 3, and then phi of 2 would be 1. So that would be feet of 366. So those are some of the ways to do this. You know, there's a lot of different ways to factor. You want to see a list of all the answers? Here's all possible answers. You just kind of applying this trick over and over again. I mean, you just look for factors of 120. So the factors of 120 are 1, 2, 3, 4, 5, 8, 9. Sorry, so 1, 2, 4, 6, 12, 20, 10, 12, 30, 60. So if you have all those numbers, you look for, you can use the fact that p of a prime is p minus 1, and just kind of piece it together. So here are the possible answers: 143, 155, 175, 83, 225, 231, 244, 248, 286, 308, 310, 350, 6, 372, 96, 450, and 462. So for all those are any three of those would have been correct answer for question 5. Okay. All right. Any questions about number 5? One thing, I mean, I noticed a lot of people when you're evaluating the phi function, you're using there's this formula. It's n times the product of 1 minus 1 over p, where p is a prime dividing n. So I mean that's true, but sometimes it's when you just have like a prime power, it's probably easier to just evaluate it as p to the n minus p to the n minus 1, which is equivalent. I mean it's the same as p to the n times parentheses 1 minus 1 over p. But this is, to me, I mean, it's often sometimes easier to just evaluate for prime power. So, any other questions? Any questions about number 5? All right. Number 6. That was, that was just like a homework question, really, about find the last 3 digits. So you take, if you want to find the last 3 digits, it's equivalent to solving mod 1,000. And then you have to use the fact that phi of 1,000 is 400, so 13 to the power of 400 we can go into 1. Any question about number 6? Okay, so number 7. So there were very few complete proofs given that there's an infinite number of primes. And I think if you look back at the tape from our last class, I specifically said you need to know how to prove there's an infinite number of primes. I don't know. Did I not?
No, you said it. I forgot to say it.
Yeah, okay. I was pretty sure that was the only problem I said for sure was going to be on the test. I was like, you need to know how to prove there's an infinite number of primes. So we proved it 4 different ways. And, anyways, so I mean, you can look back at your notes. Find one. We did a Euclid's proof. The Euclid's proof is proof by contradiction. You look. Suppose there's a finite number, and then you look at the product of the problem prime plus 1, and show that if it has a prime divisor, it can't be any one of the primes you already listed. So you get a contradiction. Then we had our first class together. We had a constructive proof where we built integers with as many. You build an integer with as many different number of I think it was like. Something like n2, n3, and so on. So these numbers, like n2 we built had at least two distinct prime factor, and we built N3, which has at least 3 distinct prime factors. You can continue that process forever, so you can always build an integer that has as many primes as you want, so there must be an infinite number of them. And then we proved 2 special cases of the primes in arithmetic progression. They're basically like Euclid's proof. That there's infinite number of primes of certain types. But anyways, so any questions about that?
I have one real quick. Yeah, I put in congruent so distinct.
Yeah.
What's the difference? I mean, I'm agreeing. I'm saying I'm sure you're. I'm just curious.
So incongruent and distinct. What's the difference?
Yeah.
So you're saying distinct primes. You said incongruent. That implies a congruency, which needs a modulus. So what would the modulus be?
I see. Okay.
I mean, primes. So you could say primes are all odd primes are congruent mod 2,
I see.
but they're an incongruent mod another modulus.
I was implying not equal. Okay.
Yeah.
I got you.
Yeah, I don't think I did one.
No. Poor choice of words for me.
Right. So, and then because we did talk about distinct solutions, mod congruence, and that just means that they're not congruent to each other. Two solutions that are not congruent to each other will be distinct solutions, as opposed to, like this has 2 distinct prime factors. This has 3 distinct prime factors. Any other questions? Number 7. Okay, number 8, I think went well. I mean, so this is, a technique. I think a lot of people actually use on homework 6 that you can prove, you can find a solution or prove a solution does not exist to a polynomial congruence just by looking at all the residue classes, all the possible residues. So for this solution, for number 8, n cubed plus 2n times 0 mod 3. All you have to do is check complete residue system mod 3. So you can plug in 0, 1, and 2 for n and show that it's always true. So if I was in like a discrete math class, I might say something like n cubed plus 2n divided by 3. So prove this is always an integer. That's one way to solve prove this is always an integer. It would be the same as saying that, okay, well then n cubed plus 2n must be 0 mod 3. It must be a multiple of 3. So you can see that proving statements about integers it can be very useful to use congruences to solve to prove theorems about integers. Number 9 was from class. We did in class. I think that one went pretty well. Just remember that, I think maybe a few people added the digits instead of took the alternating sum, like because 10 is congruent to -1 mod 11. So that's why when you add up the digits, you have to, the 3 would, the farthest to the right would be positive, and the 4 would be negative, 2 positive, and so on. So the answer, so the x would have been 2. Any questions about number 9? Number 10, also want to talk about that. So you guys are math teachers. Or if you were taking a multiple choice math test that said solve this equation and you had like 4 answers there, what kind of strategy have you taught your students to plug it in, right? So that's this equation, ax equal to b mod p squared. And I said prove that a to the power p squared minus p minus 1 times b is a solution. So you got to plug it in and show that show that this makes the equation true, or makes the congruence true. So what do you get when you plug in A to the p squared minus p minus 1 times b? Plug it in for x. Combined powers of a, you get a to the p squared minus p times b. And you gotta use, then I was hoping you'd recognize this should equal b, right? So a to the p squared minus p, that is phi of p squared. So a to the phi of p squared is 1. We went to 1. So this is b. Therefore this is the solution. Yeah. Okay. So I mean, we're using Euler's theorem here, right? And that's maybe again you might not recognize phi of p squared if you think of phi of p squared as p squared times 1 minus 1 over p, you probably wouldn't have recognized it. I mean, you just have to multiply this out and you get p squared minus p. So this is, I want to justify everything. Any questions with that? Okay. All right, any questions about any other questions on the midterm?
Is our final over everything or just?
Yeah, it'll be cumulative. Because we won't cover as much material after the midterm than we did before the midterm.
Can you go back to why A to the p of p squared is equal to 1 again?
That's the statement of Euler's theorem. So A, remember, so we're using the fact that A is 0 mod p. A is not going to go to 0 mod p. So if A is relative to prime of p, then A to the phi of p squared is going to go to 1 mod p squared. So I mean, Euler's is. That's Euler's theorem. Just to have the modulus and is p squared in this case. Fermat's theorem is a special case of Euler's theorem. Okay. Any other questions?
Is there any chance the final's going to be taken?
If there is going to be, it won't be all take home. But so some of the stuff that I'm going to cover this week on cryptography, I want to include that in the final. Sometimes some of the stuff is easier done with computers or calculators, things like that, and so that might be a portion of the final take home. But we're still going to have an in-class component, most of it probably in class. Yeah, I guess we'll take over. We're in, I can't remember what number that is. The 109? And that's August 1st, right?
And yours was over everything?
I don't know.
Like the true final?
The whole semester.
Friday, one of the other stuff. Thursday.
So, yeah, I'm not really able to speak too much about the finals, it's like I haven't written finals. So, the unit final, August 1st, it's a Friday. That's, I guess it's, I mean, they switched up schedules for the midterm, so but I'm assuming since we're morning class, we'll probably still be from 9 to 11.
Yeah.
And then you have Dr. Whitaker's exam, can you maybe go big break? And that's in see, 109. Like I said, I haven't written the final yet. But you saw my midterm. It's similar level type questions from homework questions. I mean, the proofs were pretty short. I know some proofs can take a long time. I mean, the longest proof was the proof that there's an infinite number of prime numbers, and I told you that was going to be on the midterm.
We bombed.
We promise that won't happen again if you want to tell us what just
Oh,
happened.
I
learned our lesson.
purposely didn't write it before the time. So. I haven't. I know some people, you guys like study guides and things like that, right? Sure do.
A practice test.
A practice test.
That's exactly like the real thing.
Yeah, so that's usually when people, when a course is run several times, professors can say, oh, here's some old exams. And, this is the first time this class has been taught, so I still haven't built everything. So you guys already started preparing for finals, right? You guys have tons of time on your hands.
Yeah.
Yeah. I know you guys have lives, and I've got a life too, so it's hard to prepare 2 weeks ahead of time for anything in life.
You know how many more homeworks you're gonna have and how far you're gonna
Yeah,
go.
I'm only gonna do one more homework assignment. So I'm gonna post some videos by tomorrow, hopefully by tomorrow, and then I'll post your last homework assignment. My goal is to have it posted by tomorrow, and I'll be due next week. I mentioned I want to talk about cryptography, which is a very important application of number theory in modern society. I mean, all of our digital encryption, think about it, all of our commerce that's done over the internet, banking. I mean, have you ever cashed a paycheck? I mean, mine's direct deposit. I know it's just all a bunch of electrons. It's like great. My electrons just bang. I mean, there's no money anymore. It's just all. So all the digital encryption is important, and it's all an application of number theory. So I want to talk about that. So today we're going to talk about classical crypto systems that were used up to through World War II, and then on my videos this week I'm going to talk about more modern cryptography, specifically the RSA algorithm. So I'll do a homework assignment. Hopefully by tomorrow we'll get that posted. That'll be the last homework assignment. Next week I want to talk about prime number theorem and distribution of prime numbers, which is very classical number theory, and maybe talk about Riemann hypothesis a little bit. Just kind of finish up the course with some interesting topics. I don't think I'm going to give a homework assignment to them. It's just so late, and it's going to be more difficult topics too. So it's going to be more analytical number theory. So anyway, so that's my goal is to have one more homework assignment posted hopefully by tomorrow. So now I know you guys mostly wait to Wednesday to do your homework, turn your homework in. So you guys start your homework on Wednesday. If I post it tomorrow, will you start your homework for the next week before you turn in homework 7? So that's my goal is to get it posted by tomorrow, but I know you guys wait. Okay, so that's the goal. I'm going to do hopefully at least 2 videos this week, hopefully 2 videos next week, one more homework assignment, and then we'll have final exam on August 1st. I can try to do like a study guide or something.
I guess what would be nice is that since the last exam was the midterm and it took us 2 hours, and now you're adding material to it, plus that material, it's still only 2 hours. If you could maybe narrow down the topics a little bit.
Yeah, nobody didn't. I think everybody finished it in 2 hours.
Yeah.
So I would make the test. I don't have to test the same skills that I tested on this one. I'm not going to give you the same type of exactly the same type of question, for example, but, I'll test all the, I mean, I think about, if you go back over your notes and over your homework, and see the big
Didn't you send out an
themes,
email?
big theorems.
Did you send out an email about the study guide?
I didn't give a study guide.
You sent me an email that said,
Exactly what's on the test, yeah, you shouldn't have told everybody that.
What did I say? You sent me an email, and in the email it said, make sure you know the proofs of infinite primes, and you said, be sure to go over your, I think I might have emailed you and just said, are you going to send out a study guide? You said, I'll do it later today.
Were you not in class, the last class we had on campus?
I was, but then I asked you just, I sent you an email and just
Study
asked you
or-
if there's going to be something for me.
Oh, like a study guide?
Maybe you didn't send it out to everybody. But
I know I didn't tell you anything, I didn't tell the rest of the class.
Yeah, it was the same thing you said in class. It was just, make sure you
You
get
just
this.
didn't study it.
Study your homework or
I was
questions,
hoping
like
if I asked the
homework
second
questions.
time, I might get a little more out of
I should have said, watch YouTube.
Watch YouTube. Watch YouTube. Refer to same video.
All right, any questions about the rest of the course? I mean, like I said, I could probably try to get a study guide, but I don't, it's just more work for me, so I hesitate to commit to that right now.
Is there any chance your grading scale will change some more? Cause like this is my
If you guys all,
best grade, but yeah.
it's
my
like
worst
collusion, if you guys all bomb the final together on purpose,
grade. No,
I don't want to.
your scale's a lot higher than everybody else's. Like,
Right, but I think the material's more accessible too, and there were A's on the midterm, so I don't know how, I haven't talked to Dr. Wicker about his tests and things. I know his scale is, it seemed to me pretty generous, so,
Yeah.
again, I haven't committed myself to a certain grade scale, because I wanted to see how the midterm was.
Like Barbara said, if you get a C, you need to jump off the bridge out there.
He said that?
That's what I heard.
He said if you get more than one C, they'll ask for like the program.
Well, graduate school, you're supposed to have, the 3.0 average. But I didn't know there was isn't there like a grace period or a probation period or something like that? So it's like after this is your first term, right? I mean, so usually, I don't know, when I was in grad school, I think it was like you get a 3.0 each semester, but if you dip below that, you have like one semester to bring it up. I just don't know the policy because everything's new. But like I said, it won't get any harder. I mean, my grade scale won't go up. Like right now, it's like 85 to 100 an A. I mean, it won't be any. I'm not gonna say, everybody did great on the final. I'm gonna bump that up to a 90. It's always it's the lower down. It will get lower, but not higher. But I think, you guys have more experience now. You have more experience with these topics. You have more experience taking my tests, and so I feel like it gives you more insight on how to prepare for the final. I'm not going to change. This is what I do think. I think number one. It could have been exactly a homework problem. Number 3 could have been exactly 4 exactly homework problem. 6 was exactly homework problem. 7 we did in class. 9 we did in class. And so I think. I don't think this was an unfair test. I don't know how you feel. That's my goal. I try to build fair tests. I don't want to. I want to see what you know and see if you can use the. I don't want you to just memorize stuff. I didn't really want you to memorize infinite number of primes proof, but I want you to be able to use the knowledge to solve similar type of problems and proofs. So that's, kind of the same type of stuff will happen on the final. Any other questions, concerns?
If you did give a partial take-home final, when would you post that?
Yeah, I'd probably give you at least a week before the final. If I don't post a homework assignment, so I'll post a homework assignment next week. I could try to, instead of posting a homework assignment, maybe I could post like a problem or two for the next Wednesday for the take-home final. So you'd have at least a week to work on it, and you turn it in like probably when you come to take the final, you turn it in. So I'll give you at least a week to work on any take-home portion. Okay. Any other questions? Okay. Then homework. I want someone to talk about homework. Homework 6. They're saying back to 9.
Number 2.
Really?
Could I just kind of get a printout of it?
Yeah, that's fine. That's fine. I mean, I use.
Everybody else
Right.
is on that.
Everybody else have it? Fine. Okay. So homework 6. Polynomial congruences and then quadratic residues.
Wait.
Okay. Number 1 went fine. Number 2, everybody got the right answers. Not always the correct word to show those answers. Like X is congruent to 51 mod 2.5, so magically it's also congruent to 128. Okay, so is there questions about number 1? About number 2?
I had a question on number 2. You wrote something online about setting factors equal to 0 or something.
Right. So you guys, you've seen this in your math teacher, right? So say 3x plus 2 equals 0. I'll make it plus 2. Let's see that. Okay. So you say you have say solve this equation. I say I'm gonna go add 2 to both sides, factor this because it's much easier to factor. And set each one equal to 2. Right? Ever seen that before? You know it's wrong, right? Okay. So why is it wrong?
Because 2 factors of 2 aren't guaranteed to be 1 and has to be 2.
Yeah, I mean, exactly. So there's no 2 product property. There's only a 0 product property of algebra. But the same thing works for congruences. You can't just, if this was congruent, you can't say, okay, well, X is congruent to 2 or X minus 1 is congruent to 2. I saw several people trying that trick. Because this is easier to factor. So that's what happened. And then somehow, since the numbers were kind of small, I think like things actually kind of worked out at the end by doing this trick. But it doesn't. You can't do that. But we did have. I kind of built up these 0 product property in one of your homework assignments. Right, like if if you had. So anyway, so this was number 2 we're looking at.
X cubed.
Yeah, so if you have x cubed minus 3x squared plus 27, and we're trying to solve this, set this equal to 0 mod 225, right? So the theorem was, this has, since 225 is composite, this will have solutions exactly when the solutions model the prime factors. The congruences with the modulus equal to the prime factors also are solvable. So like 5 is a factor of this. If this congruence is not solvable mod 5, then it would not be solvable mod 225. And if it's not solvable, what's the other factor? 3. So if it's not solvable mod 3, then it's not solvable mod 225 either. So the trick is you can solve them mod 3 and mod 5, and then build back up. That's kind of the way to go. So, and if you break this down, say mod 3, if you're solving mod 3, well, this is 0 mod 3, this is 0 mod 3. So you just get f congruent to 0 mod 3. Well, there's only one solution that 0, so x is congruent to 0 mod 3. Okay, so every answer to the original congruence will be a multiple of 3. If you saw this mod 5, it's you can still factor this. If you wanted to factor it, I would probably reduce this mod 5, so this would be plus 2. This does factor, but remember how I solved, just like on the midterm, we're solving congruence mod 5. There's only 5 possible residues. You can just plug in 0, 1, 2, 3, 4 and see which one's the solution. The only solution is x equals 1.
How does it factor? Do you care to show us that?
Yeah.
Yeah.
I
I
would
just
do
broke
that
it down,
for-
honestly, and just plugged in 0, 1,
That's
2,
what I
3,
usually
4.
do.
Yeah. It factors like this. And once you have it factored, you can, now you have a 0 product property, so if this times this is going to 0 mod 5, then that's, I think it's called Euclid's lemma. I mean, if a prime divides a product, then the prime divides one of the factors. So then you can set each one of these equal to 0. You get x equals 1, or x equals 1. But this one has no solutions, mod 5. So that's why you don't get any solutions here. So the only solution, again, is x equals 1 mod 5. I mean, you could bust out all kinds of stuff like, you know, synthetic division or Kalman division, or when you find 1, 0, you could have graphed this and found a 0, and then you find a 0 at 1, and then x minus 1 is a factor, divide this by x minus 1. I mean, you can do all that, or just plug in 0, 1, 2, 3, 4. Either way, you get. So what we have is that the solutions to the original congruence are going to be 0 mod 3 and 1 mod 5. And if you look at all the possible residues between 0 and 225, you only get those 3.
Is there any easy way to find those, or do you just have to list them and start charging through?
Well, it's the Chinese remainder theorem, but
Okay.
so you could use that, and there's formulas, but I think sometimes it's just easier to do. So another fact is it's 1 mod 5, so there's a lot of multiples that are 1 mod 5 between 1 and 225. But if I solve the congruence mod 25, you get the same solution. Because I reduced 27 is still 2 mod 25, and so it's still 1 mod 25. So that eliminates a lot of possibilities. So now if you only look at numbers that are 1 mod 25, there's a lot fewer of those. So that could be a little easier way. And so you look for all the numbers between all the residues.
And you can do the same as 9, couldn't you? So you do mod 3, do mod 9.
Yeah, you would get, if you saw this mod 9, you would get x is 0 or x is 3 mod 9. So if you look at the way I saw it first mod 5, and then I said, well, actually I can do this mod 25. It'd be easier because there's less numbers to check in the end. Because now there's only 9 possible numbers you have to check. So if you list out all the numbers that are 1 mod 25, and then which ones are also multiples of 3. But then, again, to check your answers, you plug these back in the original congruence to make sure they check. But I mean, I told you, I gave you those answers because I know this one was a little bit harder. So, I mean, this is just kind of an easier trick, right? So if you just kind of multiply it right out, all the answers that are 1 mod 25. So it doesn't take that long. That's the last one. So those are the only possible answers, and then which ones are multiple of 3, 51, 6, questions? Number 3, everybody did fine with Euler's criterion, which is funny that everybody did Euler's criterion fine on number 3, but the next, number 5, we jump down to number 25, to show that, number 5, to show that the answer was that it's not solvable. So x squared plus 5x congruent to 12 mod 31. So what I wanted you to do is complete the square, and you would end up with a congruence like this: y squared congruent to 26 mod 31. Right? And so almost everybody listed out all the residues. Well, I guess plus or minus 1, plus or minus 2, plus or minus 3. And you squared them all out up to 15 and showed that none of them are congruent to 26. So that's a correct solution. But you could have just done one calculation. You could just use Euler's criterion, like from number 3. So you do 26 to the 31 minus 1 over 2, and you see that that's congruent to negative 1 mod 31. So you could have done one calculation instead of 15 calculations for number 5. So, I mean, again, like number 5, listing out all the, basically you guys found all the quadratic residues mod 31, and you showed that 26 is not a quadratic residue. So that shows that this is not solvable. But, think about, if you maybe wondered like why these guys came up with these theorems, like the law of quadratic reciprocity. When Gauss and all these guys were looking at these problems, they didn't have graphing calculators. So if you're looking at small primes, all these big theorems aren't really that necessary. But when you're talking about really large primes, like into thousands or millions places or whatever, I mean, looking at really large numbers to see if they're prime, then these theorems really came to a big aid. I mean, you saw like we did like Legendre symbols and Jacobi symbols. You can have really, really huge numbers, and those properties simplify them very quickly down to really manageable numbers. So
that was a question I had on this one. The 26 to the 15th power is an outrageous number.
Right.
So to get it, then when you divide by 31 to see if it's one less than a multiple of 31, you still get a really large number. So what I did was I broke the 26 to the 15th power into powers of 5s, and did that. Is there a better way to do it?
Just put it in the internet and on some like Google search or something,
But we don't have it on a test.
right? So,
Thanks for that encouragement.
so I would make it more manageable, make the numbers more solvable. But you did it, you did it right. You can, instead of trying to do it all on, like Mathematica I have on my computer, and that's like these computer software, it's just a lot easier to do this in one. So I just plug that in, and it tells me it's negative 1 mod 31. So, right, what he's saying is, you break this up into smaller powers. You said
5s, just 3 5s.
So this is 26 to the 5th cubed, and you can figure that residue. What was that mod?
I forget now.
It's got to be negative 1.
Yeah. Yeah, negative 1 cubed to be negative 1. Yeah.
So, and then, something like that. It doesn't have to be negative 1. It could be something.
It could be,
And also, when you cube it, it's going to be negative 1, not 31. I don't know if you remember. Does we have a calculator? You can figure that out. It's 26 to the 5th power, mod 31.
6.
So 6 cubed is what? 16. Should that be, is that negative 1, mod 31? I mean, it should be. I didn't work it out this way. Yeah, it's 217.
Yeah.
That's 7 times 31.
Yeah.
Yeah, so this is 9. So that's a way you can do it to keep it, the calculations more manageable. So again, because you can always replace any integer with its residue. So 26 to the 5th is congruent to 6 mod 31. So you can replace that number with 6. 6 cubed. So that's a good thing to point out when you're doing these kind of calculations. Okay, so number 3, I guess my point was that you could have used Euler's criterion in a later problem to show that 26 is not a quadratic residue of mod 31. You could have used Jacobi symbols or Legendre symbols. I mean, you could have whatever, but you didn't have to actually. If I said find all the quadratic residues mod 31, then what you guys did, that's the way you pretty much have to do it. You list them all out. So I skipped number 4. So number 4. So just like I did in the video, I used one example to build another example. So you will use the answers to 4A for part B. So 4. Any questions about 4A? There was a theorem I showed you that if you have a prime congruent to 3 mod 4, then you can just automatically have a solution, right? So if P is congruent to 3 mod 4, then A to the P plus 1 over 4 is a solution. That was the theorem you could have used. In this case, it would be 10 to the 31 plus 1 over 4. 10 to the 8, and that's congruent to 14 mod 31. So if 14 is a square root mod 31, then negative 14 is also a square root. Those are the 2 solutions. And part B, you solve the congruence x squared. You're going to 134, so reduce it to 1 mod 7, and then the other one was x squared. We're going to 134, which is congruent to 10 mod 31. We solve those. So here we know the only solutions are plus or minus 1. And here we already used part A, so x is congruent to plus or minus 14. And then again, you could bust out the Chinese-Germain theorem, or as I kind of showed you, just writing out residues that are congruent to 14 and negative 14 mod 31, and then looking to see which ones are also either plus or minus 1 mod 7. And so there's several ways to write the answer. If you want integers mod 217, you could write them as 48, 76, 141, 169. But a lot of people didn't have to answer that way, but it's still correct. Right? Because 48 and negative 48, 76 and negative 76, you could write it that way. You could say plus or minus 169, you could say plus or minus 141. So there's several different ways you could write the answers. Okay.
Why did I not get 48 and 76?
Did you get these two?
Yeah, and I got the plus or minus.
Those are the same. I mean, because negative 169 is going to be 48, convert to 48.
Oh, okay.
And then negative 141 is 76.
But it's okay if you just wrote
Yeah.
plus or minus.
Yeah, either way, it's fine. Any other questions about number 4? So 5, I already went over that. The main thing is, if you're going to complete the square, you need an even coefficient here. So you just add 31 to this coefficient, and then complete the square. Any questions about number 5? Okay. Number 6. So I think number 6 looked a lot harder than it really was. So it's just, if you did a proof by cases, there's like 4 cases, and you're just using the properties of the law of quadratic reciprocity and properties of Jacobi symbols, or the Legendre symbols, and it wasn't that bad. So I'm just going to show one case. There's 4 cases, and they're all about the same. So we had 4 cases. So my cases were P congruent to 1, so plus or minus 1 and plus or minus 5 mod 12. So I'm going to show you one case. So if P is congruent, so case 1, P is congruent to 1 mod 12. So P is 1 mod 12, it's also 1 mod 3 and 1 mod 4. Something you should know. So P is congruent to 1 mod 3 and P is congruent to 1 mod 4. Okay, so this is important for the law of quadratic reciprocity, because if you have a Legendre symbol, if either the top entry or the bottom entry are congruent to 1 mod 4, then you can flip the entries and you don't have to introduce a negative sign. So start out with this guy, and since P is 1 mod 4, when I flip it, I don't need a minus sign. So this is about the law of quadratic reciprocity. But P is congruent to 1 mod 3, so I can replace P with its residue, mod 3. And 1 is a square. 1 is a perfect square. 1 squared is 1. So this Legendre symbol will evaluate to 1. So the other 3 cases are very similar. Like if this was minus 1, then P would be minus 1 mod 3 or 2 mod 3, and it would be also minus 1 mod 4 or 3 mod 4. So and then if P is 3 mod 4 and 3 is 3 mod 4, then when you flip it, you'd have to put a minus sign here by the law of quadratic reciprocity. And then when you replace P with its residue 2, you'd have minus, and then that 2, the Legendre symbol 2 or 3 is negative 1. 2 is not a quadratic residue, mod 3. So you get negative 1 times negative 1, and it gives you plus 1 again. And so it's just, that's the way the other cases go. Does that make sense? And then, I mean, so same thing with, you could solve it this way. Law of quadratic residue, I mean, Gauss and these guys, they came up with a kind of a, and you could have also used this formula. So, I mean, you could do it this way too, but it would work out the same way. You'd still be able to evaluate using these facts. Well, if P is 1 mod 4 and things like that, you could get either plus 1 or minus 1 here, and then using the same things, you get a plus 1 or minus 1 here, then you'd still be able to evaluate 3 over P. Okay, so either way you want to use the law of quadratic reciprocity, you still, basically, I think the best way to do it is just break it into those four cases and just simplify each case. Okay. So if you wanted to use this formula again, like you would just replace P with 1, and then this would equal 1, and then this would be even, so negative 1 to the even power would be 1, and so you would just get 3 over P equals 1. So these Legendre symbols, I mean, they came up with this notation 200 years ago. So I saw several people kind of like write them as like fractions and things like that. So just remember, I mean, don't just leave it like a fraction. I mean, it's really, you need these parentheses around it to make it look like a Legendre symbol. Probably a better way to do it now, but it was just tradition the way they did it. Any other questions about number 6? Okay, 7 and 8, I think went fine. I mean, it's just practicing using those properties of Legendre symbols and Jacobi symbols. If you're off by, sometimes it's easy to lose a minus sign or whatever, but just try to be careful when you're doing those. Any questions about 7 or 8? And there could be more than one way to solve these. So you compare your work to somebody else. I mean, you could have both done it correctly with different solutions.
On 8B, or 8A, B, and C, do we need to say if it was a residue or non-residue? Or do we?
No, I don't think I even asked. I just
No,
said,
you didn't.
just said evaluate.
Okay.
Yeah. So and as I pointed out, if you have a Jacobi symbol, if it's -1, you can be sure that it's a quadratic non-residue.
Yeah.
But if it's +1, you don't know whether
Yeah, it's on
It's a
8B.
maybe.
it's a maybe, right? Because
Now, the properties on the Legendre, can you use all those properties in Jacobi?
yes.
But you can't use some of the properties in Jacobi and those.
Well, yeah, the properties of Jacobi, you wouldn't have to use them for Legendre symbols because like Jacobi symbols, you have composite odd numbers in the bottom entry, and that doesn't happen with, just by definition, the Legendre symbol only has prime numbers,
Okay.
odd primes. So, but really, you just use all the Jacobi properties, and if it happens to have a prime over prime, it's technically a Legendre symbol, but all the same properties follow.
If on the final we're going to do the Jacobi symbols and the Legendre symbol, are we going to have to know like the number of the property?
No, I thought about that because I know you had. When I was like making my answer key, I had to go back and look at what number did I call that. It's not like these aren't like every number theorist calls that property 2. It's just.
Okay.
So I would probably have you just say a little phrase like, I don't know, like. When I said so.
It's like A squared.
Yeah, so by law of quadratic reciprocity, I can that's clear. Like law of quadratic reciprocity, you can say that. But like if I said like I had 4,177 over 2,819, and I wrote 1,358 over 2,819, and you just say because 4,177 is congruent to 1,358 mod 2,819. Just that easy. Maybe, you know what, so it should be.
I'll just make a legend up in the corner. It's like property 1, and then
So I should have you first list out all the properties, number them yourselves.
Shouldn't it be
And you
clear
figure
that we
out-
understand what we're doing?
Yeah, right. That's exactly. It should be. Yeah, if I can't tell what you did, where did they get that number?
We'll just say clearly.
Yeah, it's really.
It follows that.
It should be pretty clear. That's why when it's not on the top entry, it's much smaller than the bottom entry. That's when you want to flip it. You use a quadratic reciprocity, and then you'll reduce it. So it should be pretty clear.
Oh, we don't know our properties, we'll get the wrong answer.
Yeah, you won't be able to do it if you don't. Well, you could get the right answer. There's only 2 answers. So.
As long as
One. Which one am I feeling today?
Plus 1. I got 50 chance.
I want an answer. All the questions.
Oh, it was one little mistake.
Yeah.
First thing was taking one off.
Put the nail on there.
So yeah, I'll probably just stick with I just probably say values symbols. I didn't really need to say Legendre or Jacobi symbols because it's really the same. It's the same principles that are used to answer both of them. Okay, any other questions about 7 or 8? Okay. Have you guys thought about? Do you have any questions about? I was going to try to answer any questions about homework 7 and then take a break. You guys have any questions about homework 7? Are there a lot of questions? Do we need to take a break first, or there's number 5? Anybody else have any questions? So let's take a let's go real quick and then we'll take a break. 7. Somebody said number 3?
5.
Is it 3 and 5? Okay. Well, so you gotta know what those mean, right? So if I said tau van, what does that mean? What does that count?
What number are you doing? Number of,
Just in general, just
positive
a reason both of these.
divisors.
Number of positive.
Yes, it's the number of positive divisors. Sigma van, you add them all. Okay. So I think if you worked out some examples for number 3, you'd see that makes sense.
We were just having a hard time coming up with what to do with the product of divisors.
Yeah,
What
well,
notation to
I mean,
use.
when you if you multiply a bunch of divisors of a number together, what do you get? I mean, you get
Like that number.
you're gonna get that number,
Some-
but it could be some. Yeah, you could have multiple powers of it, and that's what's going on here. I mean, so if you
We
work
figured
out.
that out. We
you
should
work out
make
some examples.
notation. We're like, how do we come up with notation for this?
Yeah, you might think about it as I think I called them like complementary divisors, right? Like I mean, if you have like n, if D is a divisor, then its complementary divisor would be n over D. I mean, so like this is a divisor, then n over D will also have to be a divisor. I mean, so when you multiply all the divisors together, you're going to multiply this one and this one, and when you multiply these together, what do you get? You get n. So I mean, that's kind of what's going on. So maybe write out some examples. See why. Like pick a number n and then multiply all the numbers that divide that number, and see what you get. Number 5. So what I would do for number 5. I mean, look at some of the proofs I did for perfect numbers. Replace n with what it equals, like 2 to the m minus 1 times parentheses 2 to the m minus 1. I struggled with this when I was writing, when I was saying this, because I'd say 2 to the m minus 1, and then I'd say 2 to the m, and pause, minus 1. But you look at a transcript of what I said, how could you tell the difference, right? It's 2 to the m minus 1 times 2 to the m minus 1. So I'm just saying, plug that formula in for n, and then play around with the formula for sigma. You just gotta show that that's bigger than 2n. That's number 5. Any other questions? These aren't long proofs, so if you're getting several, like 10 different cases or something, I mean, it's not, it shouldn't be that long. I'm not gonna say anything else, but I was write the answer on the board. Anything else from homework 7? So I did these Google Hangout All-Stars and like mixed success. It's crazy. I did it on. Somebody else had a problem with like viewing YouTube.
Yeah, I couldn't get.
So YouTube works well with Google Chrome, and I've had this problem for things. I can't even open up my YouTube video manager, but if I open up in Chrome, then it works. Everything works because they're connected now.
Is there a way that you can use FaceTime?
Yeah, I mean, I guess. I mean, it's just like, if I try something and something's not going to work. And so I tried, so 2 weeks ago, I did a Google Hangout on my Mac, it didn't work. And then I had to log off, because I wasn't doing any video, but they could hear me. So I did it on my PC.
Yeah,
and
we
James was the only one
were
who
on
could
the
log
math labs, and
And
we could hear you talk, but you couldn't hear us.
yeah, and then several people, I actually got back with some of you guys. And then last week, I don't know, Nat tried to get on, but
Yeah.
It was my computer.
Whatever
I
he
wouldn't
was-
download the software.
Okay, yeah, 'cause there's a plugin you have to download first.
Yeah.
What's that?
Whatever he was sending to you was coming to me.
I was just
It's coming
posting
to
to
me,
the
too. I was
Well, you were commenting, yeah, so the whole, everybody's invited to the, and I was like, oh, whatever, we'll communicate somehow, so, I don't know. I mean, I guess, like I said, I'm kind of obligated contractually to have an office hour. I don't know if that's even helpful. to do
I
this,
got what
but-
I needed though. Like, you gave me a couple
So I'm gonna
times.
try it again tomorrow.
Why don't you just do like an email hour?
I got myself
You're
on.
reading emails.
Yeah, you guys got myself on, so you can. And that's what happened. Somebody called me last week and asked me for an answer or something, and I wasn't at home, and I said, I'll just email it to you when I get a chance, right? So, and that's, so I'll try to be accessible tomorrow. I think, I'm not sure if I actually can do it outside tomorrow morning. You guys like to work late at night too, right? I don't like to, but you have to.
I love it.
I noticed you're in the same boat.
Yeah, well, I mean, I got, two small kids and can't get it done. I used to making my videos, I tried doing it when people are awake. I just do them from like 12 to 2 in the morning. It just doesn't, sometimes it's quiet. So I think tomorrow I'll probably have a hangout in the evening. But feel free to call me anytime tomorrow or email me. I'll just let you know. I'm not sure what I have to do tomorrow. I know I'm busy in the morning.
There you go. Let's have a playground.
I saw some people and had their kids in the math lab.
Yeah, that was me.
They're like staring at me and.
I didn't have a babysitter, they had to come.
That's fine.
Yeah.
Yeah, no problem. No problem. So let's take a break. And I'll let you know when we go home. Hangout hour is tomorrow. It'll be in the afternoon, evening. Let's take a 5-minute break.
Hey. Okay. No, I did. I don't know.
I got this meeting because I got everybody's. You go to the and you can darken the scans too, except it's all right. I think it's fine.
There's no eight. Yeah, problems. So I took what you said and I substituted in the end. Okay? And then because of this, I can do this.
Combined with.
Why?
Yeah,
Well,
why
look
you
at it.
Right, exactly.
Okay. So then I use the formula for this one. Okay? But that just takes it down to that. Okay? And then this is not prime.
So now you have to.
But I can't get that formula for this
No,
one.
you can't. So you gotta use some other given information.
Well, I you told me that.
Right.
So can I?
So you have to use
Well, I understand that. But then I have this, and then I can split this one up. And I don't have to.
Well, think about where you're going.
As long as I don't make people start with, we're getting yelled at for that.
This is the
Looked at it.
and you at the bottom that is greater than
Yeah, greater than 2.
so maybe work backwards.
Alright, I'll think about it.
Well, I mean, it really makes Homework's not a problem.
Yeah, I'm just really upset. One minute. What am I going to do?
We'll just, just do some hypothetical common sense for it. I have the 30%, the top 30, they turn 30, and then the homework is 40. So maybe you have your homework average. And then put
In the homework stuff.
yeah, and then put average of your midterm, and then see, just do hypothetical situations. What do you think that what I would have to get on the common? Yeah, I was kind of surprised.
Yeah, I did. Alrighty. I really upset that I did that terrible mistake.
Well, that put them back for the indicator. Yeah, and they used to call me
For many reasons.
Yeah.
Right.
not just the hair.
That's really
Not just the double ones coming out.
Right?
so.
Sure, I had some, I didn't know that.
Well,
Well, there's no, I know.
My friend Robbie.
this one.
Yeah.
He's
Yeah,
so much, and like, he graduated from alternative school, he just kept getting sent back there. And they're like, he's like, I'm just gonna stay here, it's easier, and I can sing. So, but now he's like, he's the cool one, it's got the family, and such a great dad, you know, like.
Like,
You have perspective.
Yeah.
so our finals, his Friday, and the
I think the multiply, which means you could just take them to a power.
Right, we're trying to show alternative,
Alright.
I was thinking.
You wanna tell me how
and
it
then we got Liv Thursday.
Maybe it does.
Yeah.
goes? 3 or 5?
So,
I mean, see, each
in
of
one way,
each of
actually,
these,
Yeah, you said
this would be,
Friday.
This is requirement.
this would
Yeah.
be a piece of an eye. You know what I mean?
It's his Friday.
Yeah.
the other one, long way. No, I got down to this house. That's probably quicker.
Yeah, too. I agree.
Piece of eye.
I agree.
Here's the AI.
Yeah.
What you can do, what you can do this. Piece of eye.
See that?
AI over piece of eye, right? Which means it'd be a plus one up here.
Which one? I mean,
Minus
I
one.
mean, some of the dividers.
So what?
Right.
Yeah, stuff.
It's for the other way.
That's why I was thinking, if I use this instead.
So how do we?
I should. Did that.
That was that in
Well, this is the multiply these. You're gonna need to have, when you multiply all these, somewhere in that, have this. Cause you to get
I didn't think that was right.
Well, I think I'm better, okay. Or.
I got it.
Golf?
I said, you just
My favorite. Oh, look at that right there.
So I can think that's what.
Yeah, that's right, I didn't see it.
That's exactly what I had. I definitely see it.
Yeah. and then this end.
For the traffic.
Okay,
Okay, sorry.